Okay, let's get started. Welcome to the University of Tennessee College of Engineering Colloquium Program. My name is Lee Dodds, and it's my privilege to introduce today's speaker, who is Dr. Arden Bement. He is the director of the National Science Foundation. Arden received his PhD in metallurgical engineering from the University of Michigan in 1963. He's had a distinguished career in industry, government, and academia, including stints with TRW, the General Electric Company, and Battelle Northwest Laboratories. He also worked for the U.S. Department of Defense and the DARPA agency. His academic career included appointments at MIT and Purdue University. It was at Purdue that I first met Arden in the early 90s, where he was head of the nuclear engineering program at Purdue. He chaired an endowed professorship there, the David A. Ross Distinguished Professor of Nuclear Engineering. In the year 2001, he became the director of NIST, the National Institute of Standards and Technology. And then in 2004, he became the director of the National Science Foundation. He is a member of the National Academy of Engineering and a fellow of the American Academy of Arts and Sciences. The title of his presentation today is The Globalization of Science and Engineering, Competing and Collaborating. Ladies and gentlemen, please welcome Dr. Arden Bement.
Thank you very much, Lee, and good afternoon, everyone. I'm honored to join you during this nuclear engineering colloquium. This has been an amazing morning for me, learning about the achievements here at UT, especially in science and engineering. And I came to learn during my orientation this morning that there are some similarities. The hill here means about the same thing as the hill in Washington, D.C. It refers to a tower of power. The only difference is you have one tower of power, we have many in Washington, D.C., and you have to pay attention to all of them. As Lee pointed out, I was head of nuclear engineering program at Purdue before beginning my current stint of public service. I've also practically worn out a path to Oak Ridge National Laboratory over the past 50 years. In light of the strong connection between Oak Ridge and the University of Tennessee, I'm particularly grateful for the opportunity to complete the circle at long last and visit the campus and to be able to speak with you here today. I have a special appreciation for the excellence of the University of Tennessee's nuclear engineering program, for the quality of the faculty, and particularly for the students who receive their education here. This is a valid testament to Professor Dodds and the tireless mentoring of his students. Under his guidance, the UT student design teams have become a force to be reckoned with at the annual American Nuclear Society's National Students Design Competition. Today, I will address a topic that concerns not only nuclear engineers, but engineers of all stripes and scientists and educators across all disciplines. I've titled my talk, The Globalization of Science and Engineering, Competing and Collaborating. Above all, I want to emphasize the need for fresh strategies to confront the challenging circumstances of an increasingly integrated world and to keep America at the forefront of innovation. U.S. scientists and engineers have always been known for their eagerness to turn knowledge into capabilities and quickly move on to the next challenge. And the hunger to get things to market that drives business and industry puts American innovations to work rapidly for the benefit of society and the economy. I need hardly remind you that the state of the art in science and engineering has advanced at amazing speed. In this new era, we confront an even more demanding pace, not just in making incremental changes to technology, but in creating and applying new concepts and approaches. A primary reason for this lightning pace is a more competitive, more connected world. New ideas and information emerge from every region of the globe and are transmitted with the speed of light. Research networks crisscross the globe, eclipsing geographic, disciplinary, and time barriers. In short, we are now confronted with a globalization of science and engineering. Got it. Here's a recent case in point. In late 2004, Japanese researcher Hideo Hasano reported a new class of nearly transparent thin film transistors, seen here printed on flexible plastic substrate. Only weeks later, NSF-supported American researcher John Wagner at Oregon State University announced his own results, a completely transparent resistor even faster than Hasano's, but not flexible. So the race is still on. Of course, international collaboration has always been a feature of science and engineering. The character of the research enterprise dictates openness and sharing. Today's computer and communications technology simply make cooperative discovery orders of magnitude faster, and I might add more competitive. With most of the world's scientists and engineers only a mouse click away, new knowledge travels around the globe, as I said earlier, at the speed of light. The globalization of science and engineering has not only led to stiff competition for ideas, but also for science and engineering talent and for leadership in turning knowledge into applications. For the last half-century, the U.S. has held the commanding position in all three of these areas. Yet there isn't a day that goes by without a tidal wave of references in media, government, academe, industry, and even entertainment to fierce global competition and the need to sharpen American innovation. A recent Wall Street Journal headline carried this provocative headline: China and India lure corporate research centers. The article reports a Booz Allen survey of 186 top companies in 19 countries and 17 industrial sectors. The survey found that more than 3/4 of research and development sites planned through 2007 were slated for India or China. What is causing the current stir and deepening concern is the prospect that companies are now offshoring sophisticated research and development efforts. These involve growing levels of complexity and support for leading-edge innovation and design capabilities, precisely the forte of the U.S. and the source of our own economic growth and good jobs. There can be little doubt about this trend. Sophisticated R&D will always eventually go global. Should we be worried? Perhaps. Should we panic? Decidedly not. For one thing, concerns about offshoring have failed to consider the flip side of the coin, what I like to call onshoring. Onshoring encompasses the flow of talent and foreign investment that comes into the United States. Investment in the U.S. by firms from abroad, drawn by the quality of university research and tech talent, as well as the lucrative U.S. market, has played a pivotal role in the nation's economic growth. Foreign companies that locate near U.S. universities and research parks do so for very good reasons: to gain access to superior research, better trained talent, and emerging technologies available nowhere else in the world. So far, U.S. research that moves offshore is less advanced than research that remains onshore, and we need to keep it that way. Moreover, the U.S. has long benefited from an open door policy that welcomes scientists, engineers, and students from abroad. They have made important contributions to discovery and technological innovation in our nation. To lead within the broad global context, we must continue to foster and encourage this movement of talent and investment to our shores. Even so, we have reached a flashpoint where developments worldwide are driving a new direction for America. In unveiling his American Competitiveness Initiative, President Bush stated, "America's economic strength and global leadership depend in large measure on our nation's ability to generate and harness the latest in scientific and technological developments and to apply these developments to world applications." The President's American Competitiveness Initiative is a response to the challenge of maintaining U.S. innovation and competitiveness. It lays out concrete steps to encourage innovation and to strengthen our nation's ability to compete successfully in the global economy. NSF will play a major role in this ambitious undertaking. We are one of 3 key federal agencies responsible for fundamental research in the physical sciences and engineering, slated for doubling a budget over the next 10 years. A higher level of federal investment in high-risk research will spur the generation of discoveries that produce valuable and marketable technologies, one of the principal goals of the ACI. And it will help us develop the world-class facilities and infrastructure that are essential for the kind of transformational research that can take us well beyond the current frontiers of knowledge. An equally important component of the ACI is education. NSF will help to prepare the nation's technological workforce for the 21st century, while working with educators to provide America's children with a strong foundation in K-12 science, technology, engineering, and mathematics. Adequate preparation of our students is a prerequisite for sustained innovation. The potential to maintain momentum toward path-breaking discoveries rests on the next generation of fresh talent. We need to reach all Americans with the math and science education necessary to survive and thrive in a high-tech global environment. As the President has said, we must ensure that America's children succeed in life and that America succeeds in the world. These policies aim to fortify our current strengths and bolster our prospects for sustained leadership in the future. Of course, government, industry, and educational institutions all share the responsibility for making these changes. Nothing less than the future of America is at stake. And yet, as the old saying goes, the devil is in the details. How exactly can America meet the new challenges of globalization more effectively in a time of dynamic transformation and global integration? There is no simple answer to this question. In a radically changing world, we need to be as innovative in our thinking about new paths as we are in producing iPods. Some overarching strategies can guide us in our search for new paths, namely an unstinting focus on the frontier, the use of strategic experimentation, and the pursuit of collaborative advantage. At NSF, we focus on the frontiers of knowledge, identifying emerging areas that have the potential to transform an entire field of research and perhaps even an economy. There's an analogy here to the role of innovation in industry, what the Austrian economist Joseph Schumpeter identified as creative destruction, the disruption caused by technological change. The transformations brought about by computer and communications technologies are stunning examples, altering the structure of the economy and nearly every aspect of our lives. Perhaps even more importantly, these technologies have enabled us to scan research frontiers at velocities that are order of magnitude faster than ever before, spurring the creation of new knowledge to generate further innovation. As research tools, these technologies are not simply faster, they are also fundamentally superior. They have raised the level of complexity we can penetrate and harness. Just consider two revolutionary innovations in the researcher's toolkit: computer simulation and visualization. Here's a simple snapshot, I say simple, of a tornado that touched down in Illinois in 2003. The image is a visualization of a massive simulation created by researchers at the NSF-supported National Center for Supercomputer Applications, or NCSA, that portrays the development of a supercell in a subsequent tornado. According to NCSA, the simulation produced 650 billion bytes of data consisting of snapshots of the evolving storm every second during the storm. These snapshots integrate wind, temperature, pressure, humidity, turbulence, water, and ice values. The effort will help investigators analyze the process of tornado formation, a phenomenon that is not yet well understood. The tragic tsunami, hurricane, and tornado events of the recent years, demonstrate that accurate prediction of unusual weather-related events is critical to saving human lives as well as reducing economic impacts. Understanding atmospheric data and events is an extremely complex process. It brings together data from numerical weather models, Doppler radar, aircraft and balloon observations. Observations span a large variety of scales, ranging from the size of dust particles and water droplets to hundreds of miles for large storm systems. The challenge is to take this sea of complex information and present it to atmospheric researchers and weather forecasters in a format that can be easily understood and explored. NSF-supported researchers at the University of Oklahoma have also developed new weather visualization techniques to create photorealistic images of both measured and modeled data. The images use our natural experience of looking at clouds and storms to enhance understanding of weather data and to train weather spotters and forecasters. In April 2006, a globe-spanning constellation of 6 satellites headed into orbit. These low-orbiting satellites, called cosmic, will be the first to provide daily atmospheric data in real time over thousands of points on Earth. These data will be used for research as well as operational weather forecasting. The aim is to improve weather forecasts, to monitor climate change, and to enhance space weather research. COSMIC will produce a flood of new data to add to the already burgeoning databases supporting atmospheric research and weather forecasting. Climate models will eventually encompass not just atmospheric, but also oceanic and terrestrial data. Massive databases such as these are now the norm for progress in many fields of science and engineering, including the life sciences. The same tools that help us at geologic scales also give us insight at the scale of atoms. For the first time, researchers led by Klaus Schulten of the University of Illinois at Urbana-Champaign have visualized the changing atomic structure of a virus. They have calculated how each of the virus's 1 million atoms interact with each other every femtosecond. That's 1/millionth of a billionth of a second. Using a supercomputer at NCSA, the team ran a simulation about 100 days to generate just 50 nanoseconds of virus activity. It would have taken the average desktop computer 35 years to come up with the same results. The satellite tobacco mosaic virus used in this simulation is a very simple plant-infecting virus. Ultimately, using the next generation of petascale supercomputers will enable scientists to generate longer simulations from bigger biological entities. NSF is already on track to begin development of petascale computing capability. University of California, Riverside professor Ludwig Bartels and his team have designed and simulated a molecule that can walk across a flat surface in a straight line. Indeed, the molecule, called DTA for short, can walk for more than 10,000 steps on molecular appendages that act as feet. This is supposed to be a sequential slide, but it's not responding. The molecule design simulations and visualizations were done using one of the supercomputers located at the San Diego Supercomputing Center, part of the NSF-supported TerraGrid. Such a DTA nanowalker, incidentally, if this were working, what you would be able to see is a plan view of this copper surface and molecules coming and depositing on the surface and actually walking across the surface in a straight line. So this kind of a nanowalker could form the basis of a molecular memory 1,000 times more compact than current computer memory devices. And that in turn could make it important to the nascent field of molecular computing, a forerunner or a front runner for the next generation of IT. The new concept of molecular propulsion may also have far-reaching benefits for the development of surface nanorobots. This could have applications ranging from information storage to the control of surface chemical reactions. So now we have come full cycle. Empowered by revolutionary advances in computer and grid technology, enabled by sophisticated cyber infrastructure, and driven by new nano capabilities, path-breaking research like this could transform current paradigms of information technology. Without a focus on the frontier, the U.S. may not have emerged as a technology leader in computer, information, and communication sciences, or in biotechnology and in nanoscale science and engineering. We need to keep a steady eye on the frontier to sustain that leadership. As widespread and breathtaking as the IT revolution has been thus far, there is still no indication that it has reached its vast potential. Biotechnology has created a similar, if not quite so obvious, revolution. Here the results can most readily be seen in medicine, health, and agriculture, but industry has benefited as well. Nanotechnology, on the other hand, is still in its relative infancy, with huge prospects for applications in nearly every sector and for transforming manufacturing itself. Info, bio, and nanotechnologies are proving to be core capabilities for the 21st century. And to these we can also add neurotechnology, which is also advancing at a rapid pace. The rapidly advancing field of nanotechnology is a prime candidate for a second strategy to support innovation, what I call strategic experimentation. In emerging areas of great promise, there are always a variety of platforms and methods, often of equal merit, that might prove fruitful in discovery. A narrow focus at this stage is risky because betting on a single thread automatically locks out others. Perhaps more fruitful possibilities. Let me illustrate. One of the biggest challenges in the push to develop hydrogen fuel cells to power cars, cell phones, and other devices has been finding ways to store large amounts of hydrogen at the right temperatures and pressures. At UCLA, Omar Yaghi and colleagues, along with colleagues at the University of Michigan, have demonstrated the ability to store large amounts of hydrogen in concentrations of 7.5% at the right pressure. That figure exceeds the U.S. Department of Energy's estimate that hydrogen fuel will require concentrations of at least 6.5% to be practical. And carbon nanotubes have a similar potential. The key to this discovery is a class of new materials called metal organic frameworks, or MOFs for short. These materials can be made highly porous, with pores on the nanoscale, and this increases their storage capacity. 1 gram of an MOF has a surface area equal to a football field. With the promise of nanotechnology, we can anticipate systematic programs to identify or design a broad spectrum of materials with just the right properties for the application in mind. Assemblon Incorporated, a startup company formed by researchers at the University of Washington's Engineered Biomaterials Engineering Research Center, or UWEB, is producing another new material with significant potential for storing and distributing hydrogen. UWEB researchers developed the new material comprised of novel self-assembled monolayers, and then they formed Assemblon to produce and market it. The material allows hydrogen to be chemically stored at normal temperatures and pressures and then released to generate energy when it is needed. Once hydrogen has been released, this material can be recycled and reused. So it has regeneration potential. Both Yagi's and Assemblon's materials can be assembled from inexpensive ingredients. They point the way to a new capability that's critical for deploying hydrogen-fueled cars and for achieving greater energy self-sufficiency in the U.S. A richness of platforms and options is critical to innovation. Yagi has shown, for example, that MOS can store large amounts of carbon dioxide under ambient conditions. This development could be used in applications to capture carbon dioxide emissions from power plants and automobile tailpipes. We cannot predict which approach will eventually yield results, but we can assemble a portfolio of high-quality projects that approach the same frontier from different directions. Results provide feedback that then informs the next round of experimentation in an iterative process that is familiar to the science and engineering community. NSF uses this strategy to identify and support the most innovative ideas and concepts. The science and engineering community supplies the ingenuity. The best tech innovators in industry are now following a similar strategy. I have a final example to share with you that puts education in the mix. NSF-funded computer scientists and nanotechnologists at the University of North Carolina recently collaborated on a development of new computer visualization techniques that were then used successfully to rapidly explore hypotheses in a series of carbon nanotube studies. The work had another significant payoff. Besides furthering the study of nanotechnology, these visualization tools enabled middle school and high school students to directly perform cutting-edge experiments. The NSF Research on Learning and Education program at UNC brought the interactive three-dimensional graphics to school science classes. The goal was to investigate the impact of such tools on learning and the students' view of science and scientists. The students wholeheartedly embraced the experience. The next generation of highly skilled and talented university and industry researchers will come from students exposed to cutting-edge discovery. We need to be as persistently experimental in education as in discovery and technology development. We might well ask if industry shares the excitement felt by the research and education community about these new research tools and capabilities. The Council on Competitiveness just released a study on a program that paired businesses with NSF supercomputer centers around the country. All of the 40 businesses participating in the study reported that partnerships help boost innovation and their ability to compete globally. Industry participants said that they view the NSF supercomputer resources as national treasures that can be leveraged to help American companies increase their competitive edge in the global economy. And I'm convinced that companies affiliated with the Oak Ridge Supercomputing Center would have the very same to say. Now, the flip side of competition is collaboration. Although they parse as opposites, these two are turning out to be kissing cousins in this new era of science and engineering. Over a decade ago, Harvard Business School sociologist and management consultant Rosabeth Moss-Kanter identified collaborative advantage as a key strategy in a highly competitive environment. In this global economy, she writes, a well-developed ability to create and sustain fruitful collaborations give companies a significant competitive leg up. Her study of international corporations yields three fundamental aspects of successful business alliances. Although most alliances provide benefits for the partners, successful ones also provide an option on the future, opening new doors and unforeseen opportunities. Legitimate collaboration involves creating new value together in contrast to a tit-for-tat exchange of value that already exists. Successful alliances do not flourish within command and control systems. It may seem paradoxical that collaborating more with competitors is a winning strategy. At the very least, every nation collaborates in order to compete. In our era of high-velocity change, just keeping up with new science, engineering, and technical developments requires a staggering level of global communication. But information is the least to be gained. As Kanter discovered, fruitful collaboration produces benefits that flow to all parties, benefits that cannot be obtained by any of them separately. It strengthens bonds of understanding across disciplines, sectors, and cultures. And importantly, it lays the foundation for as yet unknown opportunities for further collaboration. Of course, most of you in this room are no strangers to global collaborations, especially the nuclear engineering community. You've been doing it expertly for many years. Now, the future role of the nuclear engineering community in helping with global climate change and fostering energy independence will be considerable. Along with advances in renewable energy technologies and the increasing visibility of the hydrogen economy, our new era in energy will begin to take shape. At NSF, we are taking the strategy of collaborative advantage very seriously. That means encouraging international participation in NSF-supported research. But these boundary-crossing experiences require more than technical knowledge and skills. They rest on well-honed collaborative competencies that include the ability to cooperate and communicate across disciplines, distances, and cultures. That means bringing a global collaborative perspective to every level of education, from kindergarten to postdoc, as well as teaching the skills necessary to thrive in a diverse, globally comprehensive environment. To summarize, we need to keep our eyes steadfastly on the frontier, explore promising directions, no matter what the source, and embrace and cultivate collaboration across borders. These new strategies can help us reinvent American competitiveness in the 21st century. We want our universities and businesses to continue leading the world in discovery and innovation. That means cultivating our strengths, U.S. leadership in fundamental discovery, including the high-risk, high-reward transformational research, state-of-the-art facilities and infrastructure, and a world-class S&T workforce. At the same time, we must enhance our nation's role as a partner and collaborator in the international arena. These collaborations should have the purpose of making more candy, not raiding each other's candy shops. Those nations that encourage and perfect collaborations will thrive, while those who choose not to collaborate and remain isolated will fall behind. In the long run, the proximity that collaboration fosters will open new doors for innovation, add unforeseen value, and nurture common respect for all cultures. Thank you very much.
Okay, we have time for questions and comments from the audience. So, and please use the microphone if you have a question. Well, while you think of a question, okay, Soren?
If NSF's budget is going to be doubled over the next 10 years, could you lift the veil a little bit for maybe what kind of new programs would be available within NSF to enhance our competitiveness, maybe educational programs and etc.?
Yes. First of all, let me point out that if the budget is going to double, we're going to have to be excessively proactive each and every year during that doubling period, and we have to return value received for each increment of increase. I think you would recognize that. I can't go into our 08 budget request, but there will be new initiatives, and they will focus on the roles that I articulated of NSF as far as frontier research. Many of these will be cross-foundation in nature, so they'll be highly interdisciplinary, and they'll try to couple the various disciplines that we have. Because we see fundamentally at the research, most of these tend to converge anyway. In the area of facilities, we will have new facilities. We have a large backlog of Horizon facilities that we'll be building, but the key there is that we can't just focus on construction costs. We also have to pay attention to the recurring operation, maintenance, and R&D costs that go with these facilities. If we don't pay attention to that, it will crowd out individual and group-funded research. And we have to keep balance in the program. So it has to be very carefully managed. We will also pay attention to major instrumentation. Some of you may have seen the NRC report that came out this past year, and so we're taking a hard look at the report. In education, we'll continue to focus on broadening participation, not only in terms of underserved minorities and women, but also geographic participation. We'll continue to focus on three key issue areas. One, increasing the participation in STEM field education, starting from elementary through secondary schools, improving retention rates in undergraduate education, and improving graduation rates, both at the undergraduate and graduate levels. In other words, we want to squeeze more waste out of the system wherever we can. And so there will be some initiatives that will deal with that aspect as well. On the international front, I can say that we have increased strategic focus on our international program by moving the Office of International Science and Engineering to the Director's Office. Now, that not only gives it better visibility, but it gives them better opportunities to integrate their programs with the rest of the directorates, and that's working very well. And it will lead to even further leverage in the future that will increase our international collaborations, as I indicated. And as you know, if you followed NSF, we have now given a greater strategic focus to our investments in cyber infrastructure. And I'm talking about more than heavy metal on the floor. I'm talking about networking, talking about middleware, software, everything that goes into a robust cyber infrastructure. Furthermore, we're engaging the directorates to increase their investment with the science community to provide a bottoms-up approach to developing more robust algorithms, a better application software, and better methods for managing databases, not only creating databases, but also archiving them, evaluating them, and so forth. So those are some things that I think you can expect over the next few years.
Do we have other questions from the audience? I have a question. It's sort of a self-serving question. In the past, NSF has not been a really strong supporter of nuclear engineering-related research. They've told us when we should rely on DOE and other agencies, and I'm wondering if this might change in the future.
Well, look, the prospect for supporting research in nuclear engineering departments has always existed with regard to advanced control systems, advanced instrumentation, and things that go beyond nuclear reactor and nuclear fuel design, which we clearly will not get into because there is another department in government that has that responsibility. We won't get into fusion research, but we are very actively involved in fuel cells, in the hydrogen economy, in renewable energy. So if you look at energy across the board, to the extent that nuclear engineering departments become involved in energy more broadly, there will be opportunities for support.
Lee.
In that context.
Wait a minute. Use the microphone, please.
In the context of Lee Dodd's question, what about international collaborations in your research areas that pertain to fuel cells or hydrogen storage or whatever? Do you encourage that? There's always intellectual property issues that sometimes question whether researchers here and researchers across the globe can work effectively together.
Yeah. Well, that's a mixed situation. There are some countries that have strict enforcement of intellectual properties from a legal point of view. There are other countries that don't have the legal infrastructure to enforce intellectual properties and copyright protection. So you can guess the countries we would prefer to collaborate with. But fundamentally, what I mean by collaboration, we don't send taxpayers' money abroad to support researchers internationally. What we do is encourage U.S. researchers to interact and collaborate with their foreign counterparts. What that means is that NSF will support the U.S. researcher in return for the other country supporting their researchers, and then they'll work together. Now, even that's not enough. That project has to be peer-reviewed. Now, for countries that we have worked with very closely, where we understand their peer review system, we would accept their peer review as being comparable to the quality of our peer review. In other countries, we would expect them to meet the standards of our peer review. So it's a mixed bag at the present time, but the world is changing. There are countries all over the world that are trying to emulate the National Science Foundation in Russia and China and other countries. And almost every country now is paying a lot more attention to peer review. As a matter of fact, in early October, I'll be traveling to Prague in the Czech Republic to keynote an international meeting on peer review, and there'll be very strong participation of Central European countries, primarily because they see that as a path for their future as well.
Okay. Yes.
Hi, I'm glad to have a chance to listen to your talk. My name is Ziwei Wang. I'm a professor in chemical engineering here at university. I'd like to maybe call your attention to, if you're not very much aware, the security measure that U.S. government has taken is in conjunction, in light of the international collaboration perspective, that since the 9/11 incident, the U.S. government has been putting background check and others on prospective incoming graduate students from India, China, and others.
Yeah.
As a result, the impact on the education, we are always trying to recruit,
Yeah.
right? I don't know if NSF has any influence or ongoing dialogue. This has put a big damper on our efforts due to delays and others. As I understand it, a lot of the bright students are now going over to Europe or to Britain and so on, bypassing this. As a matter of fact, I participated in one of the STEM education proposal panel, and one of the person proposing is to look at the reasons that U.S. seem to be losing its attractiveness to graduate students in the STEM area. I said, no, we don't need to fund any proposal. I can tell you a large reason, at least in the engineering, maybe in physics area, is this extra. I understand we need extra.
Yeah.
Is there any potential resolution to this hardship problem that?
It's a balanced issue. It is an area where national security is involved, but it's also an area where scientific openness is involved, and that's a tension. Within the Committee of Science, for example, the National Council for Science and Technology, there's an interagency working group that continues to explore these issues and works closely with the Department of State to make these restrictions more flexible. But let me tell you, this hasn't happened since 9/11. Even before 9/11, the same lists were there and the same checks were made. And I can recall being head of the School of Nuclear Engineering, I had to face the same issues of trying to get top graduate students to come into nuclear engineering because nuclear engineering was a hot button. So what they did was they came in civil engineering or environmental engineering. And once they got on campus and they took one semester in that department, then they would petition to transfer their program to nuclear engineering. So they found ways to get around that. We had to clamp down on that, but nevertheless, that's not necessarily new. There's been a lot of talk about visas, and we paid a lot of attention to try to make visas more flexible. There are special units in the State Department that if a federal department makes special requests, we can accelerate visa applications because the list is very long. So there are ways to ease some of those restrictions. As I recall the numbers, as far as visiting scientists and engineers in the U.S. today from other countries, we're about 15% above what the numbers were just prior to 9/11. So it dipped, but it's come back up again, and it's now much more robust. I can't say the same for graduate students, but we're up to about 85% of what it was before 9/11. And some of that difference is not just due to visa restrictions. Part of it is free education in Germany or Denmark or Sweden. So cost of education plays a factor. And get free education in Australia as well. The other factor is that there has been enormous infrastructure investment in China and now in Pakistan and many other countries. And there's less of an imperative for very bright students to go out of country to get a quality education. So that also has played a factor. But I go back to my comment in my remarks that we need to do as much as we possibly can to have an openness to allow international students to come to the U.S. for education, and we have to lower the barriers wherever we can. I appreciate your comment.
Do we have any other questions? Oh, I'm sorry. Yes, over here. Let me get the mic over here. No, that's for the webcast.
You may be able to answer this quickly, but in regards to collaboration between business and education, we have different goals. Education, as you know, tries to innovate to publish, and a business tries to innovate to produce. And so how does NSF's programs try to encourage that collaboration when the goals are very different?
Well, we currently support the order of 120 centers, like engineering research centers, science and technology centers, centers of teaching and learning, other centers. And that's done under a cooperative agreement. And one of the terms in that cooperative agreement is that each of these centers have to collaborate with industry. They have to involve industry in their research program, but we leave it to each of the centers to figure out how best to do that. We have a program called Partnerships for Innovation. I think there's one program here at UT, which funds the university and top researchers who have an innovative bent to develop partnerships with small industry, large industry, state agencies, to facilitate the transfer of technology, the transfer of new concepts into new economic development, whether it's a small startup or whether it's working with a large company to license technology or to work collaboratively on a project. The Small Business Innovation Program and the STTR program at NSF is another case in point. We pay a lot of attention to managing those programs exceptionally well because we feel that they're critically important, and we focus the companies that we support on the emerging technologies that we provide grants to the universities, like nanotechnology, biotechnology, and other emerging technology fields. So we don't support everything across the board. And wherever possible, we encourage partnerships between our SBIR investments and our university grants. So those are some of the ways that we try to couple the private sector with academia. But I can say that in spite of all those efforts, if you look at the broader picture, industry support to colleges and universities for research in the U.S. has dropped, and it continues to drop. And that's a matter of concern.
Okay, I think in view of the time that we'll conclude the formal question and answer period. We do have a reception planned right outside in the foyer as you enter this room. And the reception does include refreshments for all the graduate students and all the attendees. Everyone's invited, and we hope that you'll stick around and ask questions one-on-one to Arden. But before we adjourn, let's express our appreciation again to Dr. Bement for his presentation. Thank you. That was wonderful. Really, it was ideal. Perfect. Thank you so much. Thank you. All right, we'll go outside.